Welcome to this presentation on data preparation for machine learning. Data preparation. Data preparation is often called the most time-consuming yet most impactful part of ML workflow. Data scientists typically spend 60 to 80% of their time preparing data. So we will cover the most important topics: why data preparation matters, feature scaling, train test split, cross validation, how to handle imbalanced data, data leakage prevention, and data pipelines. Even the most sophisticated algorithms will fail if they receive poorly prepared data. This deck gives you the foundation knowledge to build robust production-ready ML workflows. So this slide will give an overview of all the 7 topics in this presentation. Each topic builds upon the previous one, forming a logical workflow for data preparation. We start by understanding why data preparation is necessary, moving to specific techniques: scaling, splitting, validation, addressing the common challenges: imbalanced data, leakage, and finish with how to automate everything using pipelines. This structure mirrors the real-world ML project workflow. Why data preparation? Data preparation is the foundation of every successful ML project. The key reason why it matters is: first one, garbage in, garbage out. No matter how sophisticated your algorithm is, if the input data is poor, the output will be poor. This is one of the most fundamental rules in data science. Second one, time reality. Industry surveys consistently show that data scientists spend 60 to 80% of their time on data preparation tasks, not on building models. This shows how critical this step is. And third important is common data problems in real world datasets. Missing values, patient records with no blood pressure reading, outliers, a house listed at $1 versus the typical $3 lakhs, inconsistent formats, dates in month, date, year versus date, month, year, duplicate records, wrong data types, age stored as text. And fourth one is business impact. Poor data preparation leads to unreliable model that can cause wrong business decision, financial losses, or even safety issues in critical applications like healthcare. Scaling. Feature scaling ensures all numerical features contribute equally to the model. Why it matters? For example, imagine a dataset with age ranging from 20 to 80 and income ranging from 30,000 to 1,50,000. In KNN, distance is calculated between points. Without scaling, a $10,000 salary difference completely overshades a 50-year age difference, making age nearly irrelevant. So the method first used is min-max normalization. The formula used for this is x minus min divided by max minus min. Example, here age 30 with min equal to 20 and max equal to 80. So you will get around 0.167. All values become between 0 and 1. One extreme outlier can compress all other values into a tiny range. The second method used is standardization. Another name for this is z-score. Formula for standardization is x minus mean divided by standard deviation. If example age is equal to 30 and mean we are consider as 45 and standard deviation equal to 50, we will get around minus 1.0. So the result is mean equal to 0 and standard deviation equal to 1. So it better handle the outliers. So always fit the scalar on training data only. It will transform both train and test sets. Never fit onto the entire data sets. This causes data leakage. Algorithms that need scaling are linear or logistic regression, SVM, KNN networks, neural networks, K-mean. The algorithms that don't use here are the decision tree, random forest, XBoost, gradient boosting. Train test split. Train test split is one of the most fundamental concepts in machine learning. The core problem it solves are if you train and test your model on the same data, it will memorize the answers. Overfitting. It will score perfectly on that data but fail completely on new real world data. This is like a student who memorizes exam answers but does not understand the subject. So you can see how it works. Consider the training set 80%. The model sees this data and learns patterns from it. And test set is 20%. So the model never sees this during training, used only for final evaluation. Think of training data as practice problem and test data as the final exam. So random underscore state equal to 42 ensures the same split every time you run the code, and stratify equal to y maintains the same class proposition in both sets. So it is crucial for imbalanced data. For time series data, do not shuffle, preserve the temporal order. So the golden rule is the test set represents your model performance on new unseen data. If you use test data for any decision during model development, the evaluation becomes invalid. Validation set for hyperparameter tuning, you need a third split, that is training 60% and validation is 20% and test is 20%, or use cross validation instead. K-fold cross-validation is a more robust way to evaluate model performance than a single train test split. How K-fold works with for k equal to 5 we can see in this table. First step is split the data set into 5 equal folds. In round 1, use folds 2 to 5 for training, fold 1 for testing and record the score 1. And in round 2, use folds 1, 3, 4, 5 for training and fold 2 for testing. Record the score 2. Continue until each fold has been test set once. So final score equal to the average of all the 5 scores. Why it is better than the single split? A single split might get lucky or unlucky depending on which records ends up in which set. CV gives a mean and standard deviation of performance. If scores vary widely across folds, high standard deviation, your model is unstable. So the common variants are stratified k-fold, maintains class proposition in each fold. This is mainly used for classification. Leave one out, LOO. K equal to n, that is each sample is test set once. It's very slow but for tiny data sets. And time series split respects temporal order for time dependent data. So the typical k values k equal to 5 or k equal to 10 are standard. K equal to 10 gives slightly better estimate but takes too into longer time. In Skylearn, cross-val score of model x, y CV equal to 5 score equal to accuracy. How to handle imbalanced data? Imbalanced data is one of the most common and trickiest problem in real world ML. A data set where one class significantly outnumbers the other classes. That is imbalanced data. In the real world examples, credit card fraud, 0.1% fraud transactions are there. Disease diagnosis, 95% healthy and 5% disease. Manufacturing defects, 99% good products, 1% defective. Network intrusion detection, rare attack packets among normal traffic. So the accuracy paradox in fraud detection with 1% fraud always predicting not fraud gives 99% accuracy. But this model misses all fraud cases completely is worthless. So the solution is SMOKE, that is nothing but synthetic minority oversampling technique is used. It creates synthetic samples by finding nearest neighbors in minority classes, interpolates between existing minority samples from imvlearn.over underscore sampling import SMOKE. And second solution is undersampling. Randomly removes the majority class samples. Simple but risk losing valuable information. Better variants. Tomac links edited nearest neighbors are used. And the third solution is class weights. Most convenient. There is no data modification is done here. Tell the models getting a fraud wrong is 99 into more costly than getting a normal case wrong. So logistic regression of class weight equal to balanced is used. Evaluation metrics for imbalanced data is precision of fraud prediction, how many were actually fraud, and recall says of actual fraud cases, how many did we catch, and F1 square, the harmonic mean of precision and recall. AUC underscore ROC, the overall model discrimination ability. Data leakage prevention. Data leakage is one of the most dangerous and common mistakes in machine learning. Why it is dangerous? Leaked models show amazing performance in testing, sometimes 99% plus accuracy, but fails completely sometimes. When deployed in production, this can lead to wrong business decision based on false confidence. Type 1 is the target leakage. Example, predicting loan default. So first one is the bad, including collection calls made as a future. This only happens after default. This model learns that collection calls as default. Correct but useless in practice. At prediction time, you won't have this feature for a new loan applicant. So the rule is you have to use only features that would be available at the time of making a prediction. And the second type is train test contamination, most common versions. The wrong order here is with scalar on all data, split train test is wrong order, but the right order is split first, fit the scalar on train only, then transform both. So the wrong scalar dot fit underscore transform of x, then split right x underscore train x underscore test equal to split first and scalar fit of x train scalar the transform of x text function is used. Other leakage sources to watch are inputting missing values before splitting. Use the test data's mean or median and feature selection using all data. Select features that work because of test data patterns. and duplicate across train and test sets. So the best practice we have to use is Skylum pipelines. Data pipelines. Data pipelines are the professional way to package all your data preparation steps. What is a pipeline? A pipeline is an object that chains multiple data processing steps and be modeled into one unit. Instead of manually applying step 1, then step 2 and step 3 separately, the pipeline does it all automatically. The problem with manual pre-processing is without pipelines, we have to remember to apply the same transformations at training and prediction time. Forgetting a step or applying it differently cases bugs that are hard to detect. How Skyline pipeline works. Each step is a tuple, that is name, transformer or estimator. All steps except the last must have fit-off function and transformer function methods. The last step must have fit-off function and predict-off function methods. Pipe.fit-off x underscore train, comma y underscore train. It will fix all transformers on train data, then trains the model. Pipe.predict of x underscore test transforms x underscore test using fitted parameters, then predicts. So the key benefits are leakage prevention. When used with cross validation, Skylum refits the entire pipeline on each training fold. This means the scalar only sees the current training fold, not the validation fold. Examples with cross validations, cross underscore val underscore of score of 5 comma x underscore train comma y underscore train and cv equal to 5. This is the golden standard used. And production deployment, save the entire pipelines, the job lib.dump of pipe comma model dot pkl and load and predict pipe is equal to job lib dot load of model dot pkl. Pipe dot predict of new data. So the key takeaways are, what are the 7 key concepts we have covered in this presentations? Why data preparation? 80% of ML work is data preparation. So garbage in equal to garbage out. And feature scaling, use min-max, normalization 0 to 1 range or standardization, mean equal to 0, standard deviation equal to 1. Record for KNN, SVM, neural networks, logistic regression, not record for tree-based model. Train test split 80% train, 20% set. Use random state for reproducibility, stratify for classification. The test set is the final exam, never peak during development. For this cross validation, 5-fold or 10-fold CV gives more reliable evaluation than a single split. Always use stratified k-fold for classification problems. If this imbalanced data, use mode undersampling or class underscore weight equal to balanced. Evaluate with F1 square and AUC hyphen ROC, not accuracy. Sixth is the data leakage. Split first, then fit the preprocessor on training data only. Leakage causes greater training scores but terrible production performance. Seventh is data pipelines. Chain all steps into one Skylum pipeline object. Prevent leakage, ensures reproducibility, simplifies deployment. So the 7 concepts will form the foundation of this professional MLs. Thank you.